Quiet down, please. All right, quiet, please. Quiet. 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 All right, so today what we are going to do is we're going to review a bunch of the reactions that we've done. I'm actually going to cover a couple things that I had realized that I had sort of skipped over within carbonyl chemistry, and then what I'm going to do is I'm going to review the reactions that you guys have learned, and then we'll go through some synthesis. Next class, what we are going to do is organometallic reactions, as well as we'll probably end up getting to radical chemistry next week as well, although that may be for the following week. You guys do have a quiz that's coming up right next week. That's quiz number 4. It's going to be the first quiz where you guys get tested on synthesis. Okay, so we've learned a lot of reactions. Hopefully, if you guys have been staying on top of everything, by this point you have at least started to think about practicing synthesis and sort of getting the handle on that. Now, one of the reasons why I sort of rushed through these reactions is so that you guys can have time to spend a good week or so really reflecting on all the reactions and working on the synthesis before the quiz. But certainly then the exam is like basically 2 weeks from today, right? So, and that's always one of the toughest quizzes. It's always the sort of the hardest exam that I think people deal with because it's really the first time when you're asked to sort of know tons of stuff, right? Lots of different reactions and synthesis and so forth. Okay, so the 2 reactions I missed over, that I accidentally skipped over, one of them is, and these are both from carbonyls. Okay, so I'm going to discuss these very briefly. So both these reactions are going to be from carbonyls. Now one of the issues, I just want to sort of introduce this, is if you have an amine, right? Let's say that you have RNH2, and you want to take this molecule and you want to react it with, say, or we'll just make this R1, right? Let's say that you want to take this compound and you want to react it with a halogen, right? So let's pretend that we've got some big bulky base, as well as, let's say, R2 Br. Right, and I think we have a base to scavenge the excess stuff. So let's say, I don't know, diisopropyl ethylamine. Just big bulky base. It's really not important, but the point is it's just a big bulky amine base. Okay, so let's just pretend for the sake of argument that this is not going to react with this bromide, but it'll be there to perhaps sequester any acid that forms. Okay, now as you might imagine, during this reaction, the first step, right, would be that this amine would react with the R2, right, if you just sort of think about your mechanism. And what you would get to, right, is an ammonium salt such as the one that I've shown here. Right? Now, the problem with this is that you have a base here, just to sort of make things simpler, add an additional base, but certainly you could imagine this would get deprotonated, and that could either get deprotonated by this or this, but let's just do diisopropyl ethylamine just to be, sort of keep things a little bit simple. Okay, that's going to deprotonate this. Right, and what you're going to get to is your amine. And the problem here, right, and the problem with this reaction in general, right, is that now you have a secondary amine. And there becomes a certain selectivity issue here, right? Because if you have an alkyl halide, certainly it's going to react faster with a primary amine than a secondary amine. But the problem is that you'll often start getting that reactions with that secondary amine as well, right? And so it's very difficult to control alkylation of amines just one time. And so what will happen is you'll start to react. Oops, R1, 2. Right, what will happen is you'll have a second equivalent of this halide, right? If we just sort of go through that mechanism again, what you can start getting to is tertiary amines, such as the one that I've shown right here. right? And so it turns out that it can be very difficult to sort of control nucleophilic addition of a primary amine and just sort of make a, say, a nitrogen carbon bond with an alkyl halide. And so one of the things that we can do is use a reaction called a reductive amination. Okay, and as I go through the mechanism, hopefully it will make sense into why this is the case. And so what you can do is, obviously this will be a little bit different, but what you can do if you want to make just a standard nitrogen carbon bond is you can do what's formally a two-step process based upon reaction that you guys have learned. Okay? And so the first step in a reductive amination is that you take that compound, you can treat it with an amine. Right, such as the one that I've drawn here, and maybe we'll just say R1. Right, what's going to happen is that's going to do a condensation. Right, so that's going to condense on this here, as you might imagine. Right, you're going to release water. So sometimes you can use desiccants to drive this reaction. But you're going to get to that imine. Okay, so this is a reaction that you guys have seen in the past. It's simply addition in here. You can think about this. Again, as being an acid catalyzed process, just for the sake of staying consistent with what we've seen in the past. What happens is that when you generate this compound, right, it turns out that under these, say, conditions that you have, oftentimes you have perhaps an acid or some proton source. Oftentimes this reaction is run in methanol. But the point is that what you can now do is you can reduce this amine. Okay, similar to how we've reduced carbonyls in the past, right? And so this is also going to be a hydride source, okay? And so the name of this compound does have that sort of hydride component to it. But the specific reagent that we're going to use is called sodium cyanoborohydride. So it's very similar to the sodium borohydride that we've seen in the past, except that it is substituted, one of the hydrogens is actually substituted with a cyanide. So it's something like this, right? So it's sodium cyanoborohydride, so we can think about it like this. And it turns out that this is a little bit weaker, right, than your standard hydride sources, and so I'm not going to go into the particular details of this. But one of the ways that you could think about why something would reduce an imine over, say, a carbonyl, which happens to be the case, that can often drive this reaction, is that you can imagine under some of the conditions, for example, protonating that guy, making this much more electronically poor and efficient and much more likely to react, whereas protonating a carbonyl would require a little bit more acidic conditions. Take-home point here, though, is that when you perform this overall reaction, what you get to is sort of that reduction. So now you can sort of get to that primary amine, again, sort of following the workup. And so again, look back at the chemistry that we've seen in the past with carbonyls performing this chemistry. But I think for what you guys should think about and your sort of level of understanding of this chemistry should be sort of recognizing this as almost a two-step reaction. And in fact, I think I've run this reaction once in my life. And in that case that I did run it, I actually did do a two-step process. So you can almost think about this as a two-step synthetic sequence, although there are conditions where you can run it in a single pot. But just formally, you might just want to think about it as a two-step reaction. First, condensation of the imine, again, then sort of followed by a reduction. Again, the sodium cyanoborohydride is one that's very commonly used for this specific reaction. Okay, so this is the first reaction that I had meant to talk about earlier and didn't. Okay, so again, that's kind of like a synthesis problem, if you will, sort of a two-step synthesis of primary amines. Okay, the other thing that I wanted to mention, and we already discussed this reaction, but I just sort of want to make a point on it. So we talked about the Wittig olefination, right? So we talked about the Wittig olefination, right? And the Wittig olefination is a way that we can make alkenes, right, from carbonyls or aldehydes or so forth, right? And so the reagent that we use, right, oftentimes what we'll use here is, so we talked about as the ylid, but in fact you generally generate that ylid in situ. So what you have is a Wittig salt that looks like this, right? So this would be called a Wittig salt, so it's a sort of triphenylphosphonium bromide. And then you're going to use some sort of a base Okay, and so that base can be sodium hydride, that base can be butyllithium. You can imagine that base being a lot of different things. We'll just say sodium hydride. And what's going to happen is the component of these, right, the net result is you're going to have those two together and you're going to generate the illid, right? And that's going to do the Wittig olefinition. Now, the reason I'm sort of retelling you guys this is what we didn't discuss is how you synthesize this molecule here. Okay, and so the point is that you guys have actually learned chemistry, although you might not realize at this point, in which case you can make a Wittig salt. Okay, so now you know how to take this and sodium hydride, get the Wittig illid. Now the question is, how would you make that Wittig salt? Okay, and if I were to ask you guys intuitively how you might make this, you might assume that this might come through a substitution reaction. Okay, and that's that in fact is how you do this chemistry. So this is simply the way that you make a Wittig salt is that you take an alkyl halide, right? In this case, bromomethane, and you're going to treat this with triphenylphosphine. Do you guys hear that, or is that? What's that? Sounds like an alarm.
I hear it.
Well, it's just the fire alarms here, like so quiet that oftentimes.
I don't think it's a fire.
Well, yeah, except in this building, right? Okay, so let's just assume that we're not going to get stuck in a fire trap here, okay? And so what you do is you simply take triphenylphosphine and you treat it with an alkyl halide, and what happens is, as you might imagine, you're going to simply substitute that triphenylphosphine for the bromide, and you end up with this salt. And so this is a very easy reaction. You basically take these two, mix them together in toluene, heat it up, everything dissolves, then you usually just cool it down, and this salt crashes out. So it's very easy to make. But the point is that the Wittig reaction is a very useful compound, and particularly when you guys are thinking about synthesis problems, on occasion you might want to use a Wittig in your sort of synthesis. Right? It's a carbon-carbon bond forming reaction, so it could have value. In fact, it's the one of the quickest ways, this is the only way really that we know that we can make a carbon-carbon bond and have a double bond in there. Other ways that we know are a little bit different. But the point is that if you get, say, a synthesis problem, and maybe we'll see one today, where you're asked to sort of make something and have something be your only starting material, well, it might be useful to know how to make that Wittig salt. And again, it's very straightforward. This is simply substitution chemistry, and it shouldn't really look anything too different. Yes?
Sorry, but why do we need the base again?
So the base, so the active, remember that the active species in this is what we call an illid. Right? Sometimes we'll draw it as a double bond, but it's what we call an illid. The salt has CH3, so we need to deprotonate one of those. And so you use a base, and the base will come in and pluck off one of those protons. That'll give this, which is the active form. So if you take the Wittig salt and the aldehyde, nothing's going to happen. Right? You need to actually get to the active compound, which is the illid. Okay? Okay. All right, so these are the two reactions I just wanted to mention really quickly that I hadn't covered previously. And what I'm going to do now is I'm going to erase all this. And we are going to sort of refresh and just sort of go through the chemistry that we've learned. Not all the chemistry, but just the chemistry of carbonyls. We'll just sort of put them up on the board. Get you guys sort of thinking about the chemistry and the reactions that we've learned, and then we'll practice some synthesis problems together to sort of get you guys thinking about synthesis a little bit more. Okay? Okay, so review on carbonyls. Okay, so again, in general, we can sort of, I think it's always best, and I've sort of made this point time and time again, that as you guys are starting to build this arsenal of reactions that you know, it's best to sort of think about them and pair them into groups so that you're relating different reactions to one another so that it doesn't seem like everything's its own separate entity. And so that's kind of what I'm going to do today, and I'm going to go through them similar to how I think we've done them in the class. But certainly there are other ways that you can sort of build upon one another. Okay, so the first thing I want to talk about is the reductions, right? And so we learned how to reduce carbonyls. So again, this is going to be all chemistry on carbonyls. Okay, and so we've learned that if we take a ketone, right, this is one class, or let's say an aldehyde. So remember aldehyde, or ketones. So again, when you have a carbon on one side of the, carbon bond to one side of the carbonyl, and then either a carbon or hydrogen bond to the other side of the carbonyl, we have many different ways that we can reduce this, right? So what's one of the ways that we can reduce, and when I'm saying reducing, I mean down to the alcohol. Okay, so one possibility is NaBH4, right? Sodium borohydride is one of the possibilities. In fact, that would probably be the go-to method if I were to be running this reaction. Again, it's the mildest. Okay, what's the stronger version that might catch fire? LAH, or lithium aluminum hydride. It might be best for you guys to sort of think about lithium aluminum hydride. I know LAH, and I'll say LAH from time to time, and it sort of rolls off the tongue really quickly, right? But lithium aluminum hydride and sodium borohydride, like, it might be worth it. You should certainly sort of remember those structures, because again, they're very related, right? It's sort of like a first row metal, and then, boron versus aluminum with 4 hydrogens, and so you can sort of relate them in that way. And then we learned one other way to do this, right? What was the last way that was analogous to how we do it with alkenes? It wouldn't be the go-to way, but right. So some type of metal. We'll just say platinum, right, and hydrogen gas, right. So you could also do this with, say, a particular metal and hydrogen gas. Okay. Okay. So aside from ketones, we've also sort of discussed these reduction type of conditions with esters and carboxylic acids. Right, so again, with esters and carboxylic acids, these are going to be molecules where instead of carbons on one side, either carbon or hydrogen on the other side, you have a carbon on one side, then you have an oxygen on the other. And again, that oxygen can either be a hydrogen, or that oxygen can be an alkyl group, in which case you have a carboxylic acid or ester. So, okay, and so we learned a couple ways, a couple different types of reductions that we can do on these compounds. So what was the one that leads to the alcohol? Right, exactly. And so in this case, if we wanted to go all the way down to the alcohol, right, what we would use is we bring out the big guns, we'd use the lithium aluminum hydride. Okay? Meanwhile, if we don't want to go all the way, you can't really do this reaction with can't really do this reaction with carboxylic acid, right? But if you had an ester, you can stop it at the vertical here. We can also stop it at the aldehyde if we wanted. And so what's the reagent that we use for that?
PCC.
Almost. What's PC? No? So remember, what are all of these?
Reductions.
The reductions. Formally, mechanistically, what do we think about doing? Sort of adding a hydride, right? So these all sort of have some hydride component to it, right? So you guys remember? Dibol. Right, so dibol. Right, so diisobutyl aluminum hydride. So this is also a hydride source. We'll just say ALH. Sorry, R2ALH. Okay, so again, it's sort of a dimer. But it's different. Again, we sort of discussed this in the fact that you're not at the aluminum doesn't actually become hydride until you sort of fill that shell, in which case then it sort of stays on there when you keep it at low temperature. And that's important. I don't know if I mentioned this yesterday, but certainly dieball will go all the way down and can go all the way down to the acid if, say, for example, you don't keep it cold enough, right? Or if you let that sort of chelate that we discussed break down. So you need to run these reactions at very low temperatures, and this certainly represents a reaction that, at least technically, can be a little bit difficult to run the sort of first time you do it. Okay, so the point is that we do have ways that you can go directly to that aldehyde. Okay. All right, so these are the reductions to the alcohols, right, or to the aldehydes. Okay. We've also learned about exhaustive reductions, right, where we can go all the way down to the hydrogen, right? And we learned two ways that we can do this. So what we can say exhaustive okay, and we learned two different methods that we can do this. So one is a Wolff-Kishner, right? What are the reagents in a Wolff-Kishner?
Hydrazine.
Hydrazine, right? What is hydrazine? Right, so H2N, NH2, and sodium hydroxide. Right? Or what's the other one that we can do?
Zinc and mercury and HCl.
Right, so zinc mercury and HCl. So zinc mercury amalgam. What's that reaction called? Do you remember? Clemmensen reduction, right? And so again, these are two different ways that you can think about it. You may imagine, why do you learn two? You may imagine, that at some point your compound might be acid sensitive, and so you might want to use something that's a little bit more basic, or if you're doing a reaction that's a little bit more basic, sensitive and sensitive to bases, or your compound sensitive to bases, then you might want to use a more acidic-based one. Okay, we just discussed, and then sort of the other one that we learned from the carbonyl, aside from these, would be the reductive amination. I guess we could throw up there as well, right? That we just discussed earlier. So I won't discuss that here. Okay. All right. So that's all the reductions. Again, there's about how many were there? 5, 6, or so. But they're all kind of similar, right? They're all reductions, and so you may want to sort of classify them all together. Yes.
So hydrogen metal would still pass reducing to an alcohol?
Hydrogen metal.
Hydrogen and metal.
Yeah. So that's kind of, you in fact can actually get certain metals to do that. But in terms of the paper chemistry that you guys are going to do, you really haven't learned any ways that you could do an exhaustive reduction. But there are ways, and certainly there are metals that would be strong enough to actually reduce off water all the way. But I would just focus on those two for now. But yeah, that's one of the things. That's why when we talk about these metals, it's like, oh, platinum. We're just sort of throwing metals up there to make you recognize that there's going to be a difference. If you forget the metal that you have, and you're doing a synthesis problem, you only want to reduce one over the other. You can't remember the specific metal. Even if you mention, like, I want to selectively reduce this over this, and I would find a metal that would do it. That's if you forget. Okay, so exhaustive reductions. Okay, the other class of reactions that we've learned, some of the other ones that we've learned, right, are condensation reactions. Okay, and so again, these are reactions where you take, if we think about, sort of reactions where we, in essence, right, so we've learned ways that we can sort of do condensation chemistry on this, where you'll generate sort of H2O. Right? If you sort of think about that oxygen leaving, right? So these are condensation reactions. And one of the ones that we learned first, right, was sort of ketal formation or acetal formation, right? And so if you take an alcohol in the presence of an acid, right, what's going to happen? You're going to get to the acetal, or the ketal, I guess in this case. Acetal and ketal are just different terminology referring to whether you're starting from a ketone or whether you're starting from an aldehyde. So, okay. So in this case, this would be starting from a ketone, so it would be a ketal. But again, that's sort of semantics that I'm not too worried about. We did discuss, again, if you have, say, a diol, right, and you do this chemistry with a diol, I should mention that in these cases, sometimes you can get to cyclic ketals, right? So we saw this with like ethylene glycol, right? So if you have a molecule that you're sort of condensing, like say for example a 1,2, you know, something like a, right? If you do this with like say ethylene glycol, we could discuss this. You'll get to like molecules like that, right? And so, yeah.
I think the way that you convert alkenes to diols with glycol is to the osmotic chocolate.
That would be the way that you would make this.
Okay.
Right, so diols, so this is just going in the forward direction. So, but that's a good point to make, right? If you wanted to make this molecule and you want to make the diol, you can make the diol from the alkene through osmotic tetroxide, right? But that's kind of not what I'm really talking about here. So there's two other, we discussed two other kind of condensation reactions. So these are when what we're condensing onto the carbonyl are oxygen-containing molecules, so alcohols are condensing onto there. We've also learned that you can do this with amines. That alarm is horrible. Okay, so again, if you take a carbonyl, we discussed this a little bit earlier, you condense this with amines, and so we'll discuss the two different things that happen. If you have a primary amine, right, what happens is you get the imine, right, where you have that double bond, carbon double bond nitrogen, right? If you did the same thing, but instead, you now have to put a ethylene group there, just to sort of show that there's protons in this position. Certainly you would need those. If you did this with, say, a secondary amine, right, and you did this in the presence of acid, you will get okay, you can get to something like this. Okay. Quick point, somebody brought up that on my sort of list of reactions, I actually had a typo where I said HRN, so one of those R's was H. If you think through the mechanism, that's not possible. Hopefully I'll be able to update that, but you guys should be able to recognize, you know, if you sort of know the chemistry, if it's a primary amine, the whole reason why it goes to the enamine, right, is because you don't have that proton there. Okay? Okay, so these are the two sort of amine condensations on here. Okay? Now, in this realm, again, these are sort of reactions that just deal with oxidation, or sorry, in the case of previously, sort of reductions. In synthesis, oftentimes the most valuable reactions are carbon-carbon bond-forming reactions, right? So we've learned two different ways that we can make carbon-carbon bonds. Okay? Yep. Oh, sorry. Thank you. Yeah, let's just do that. Yeah, so now if we want to make carbon-carbon bonds from ketones or aldehydes, we've learned a couple ways that we can do this, right? What's the sort of very first way that we discussed? right? If you take an acetylene or some carbon-based nucleophile, right? So we'll just say R, and we'll discuss when we talk about organometallic reagents, we'll discuss how we make these. But certainly we know how to make the acetylene-based one, right? So acetylene you can imagine, but as we'll see, it's really any. So you would know how to make this one, right? But as we'll see, you'll learn that you can really make lots of different carbon-based nucleophiles when we start talking about organometallic reagents, right? And so if you take these guys and you treat them with a carbonyl, right, we're going to get addition into that carbonyl, right? And following the workup, what we'll get is alcohols, right? So it's important to recognize that you guys can generate sort of carbon-carbon bonds. In this case, this carbon-carbon bond, right? From a carbonyl. Again, the product of that reaction is an alcohol. So from a retrosynthetic standpoint, if you see an alcohol in a molecule, one of the things that you guys can think about is that you can make that alcohol through adding some sort of carbon-based nucleophile into a carbonyl, right? And so this is one way that we've learned to make carbon-carbon bonds. And we just discussed the second way that we can make them. And what was that? With a Wittig, right? And so what we can do alternatively, right, is that we can take these guys, treat them with a Wittig, right, in one of its many forms, we can obviously illid, right, so again, generated from the phosphonium salt, you take this, and in this case, you'll get to that terminal. But as we'll see, again, these carbonyls are actually pretty versatile. Sorry, these Wittig-ills are fairly versatile. And one of the things that you should remember from this is a reminder on the selectivity. So I won't go through that, but remember the selectivity. In this case, there is no selectivity. Right? But if the Wittig salt came from something that can stabilize that negative charge, right, it's going to lead to the more stable alkene, so perhaps the Z alkene, but whichever one is sterically more stable. And then, again, if you've got an unstabilized group on here, it's going to go to the less stable one. But again, the point here being we've now learned two different ways that we can make carbon-carbon bonds. And so again, from a retrosynthetic standpoint, if you have an alkene, and that's one of your targets that you're trying to generate, one of the ways that you guys could consider making that alkene, right, is using a Wittig reaction. Okay? Within the realm of carbonyls, we should also mention two other reactions that we discussed, or two other classes of reactions discussed within carbonyl chemistry. Okay, and one of them was in relationship to the recognition that an alcohol can be generated from a ketone. And this was the point that if you have an epoxide, right, you can use epoxides. Again, they're kind of similar to carbonyls in a way, right? You know, just there's two carbons instead of one, and they've got this ring. But when you think about the nucleophile adding in, the result is that you have this oxygen with negative charge on it. So they're kind of related to a certain extent, right? And so we learned two ways that we can make carbon-carbon bonds from epoxides, right? So if we take an epoxide and we treat it with a good nucleophile, so strong nucleophile. So with strong, we're going to get addition into that, right? And where's it going to attack? This carbon or this carbon? The right carbon, right? Because it's going to be sterically controlled when we have a strong nucleophile. And then sort of second step is going to be a workup with water. right? So we can make that carbon-carbon bond. Okay, so again, you can imagine the alpine nucleophile adding into that. And again, as we'll see from organometallic reagents, if you have an organometallic compound, you could add into that, or some other really good nucleophile. We've also sort of learned from epoxides, right, that you can add in the opposite direction as well. So this is sort of steric control. Well, we've also learned that if you do this under acidic conditions, right, you can actually, well, it's not as simple as just saying, oh, I want to use acidic conditions. There are ways that you can use this epoxide and get the opposite selectivity. Okay, and so if you have a weaker nucleophile, like say something that's neutral, but you catalyze this reaction with some type of an acid, right? What we're going to do is we're going to activate that side, which is going to then make this similar to bromonium formation, right? So it'll have the oxygen with the positive charge, and so what we'll get is, right, sort of activation. We'll just draw it as a Bronsted acid for now, right? But what's going to happen is it's going to be electronically controlled, right? And so we're going to get addition at the other carbons. This is one of the things that complicates epoxides a little bit, but also makes them pretty versatile. Okay. All right. So there's one more set of reactions I'm going to discuss that we kind of talked about within carbonyl chemistry. And that was oxidation, right? Sort of one of the ways that we can make carbonyls. Okay. So oxidation. Right, so we can make these carbonyls through an oxidations of alcohols, yes?
When you say nucleophile, do you mean a carbon-based nucleophile?
So it would be very difficult to do a carbon-based nucleophile, right? Because a carbon-based nucleophile is going to be generally very basic, right?
How many active carbon
I didn't say carbon-carbon. Oh, maybe I kind of alluded to it. Yeah, so that's not, you're probably not going to generate a carbon-carbon bond through this. So that's probably not carbon-carbon. There may be ways to do it that I'm not sure about. There may be, like say for, actually there may be, like there are carbon-based nucleophiles that you guys really haven't learned about. Like there are, say, this is again a little advanced, but just, if I show you this, if you want, you can use it. I'm not going to test you on this, but here's one option. Right, so if you have like allyl trimethylsilanes, these are actually nucleophiles that can work in the presence of acid, and oftentimes it's acid that will mediate these. Okay, and so the reason for that is that a carbon-silicon bond, you can sort of think about this as being a resonance form. Right, and so it turns out that carbon-silicon bond stabilizes that carbocation really well, and so in this case, what you can get is what's called an allylation. And so if you added this to, say, an epoxide catalyzed by that process, what would happen is you would get something that would look like this. Okay, so there are ways to make carbon-carbon bonds this way. You guys just haven't learned any. And obviously I'm not going to hold you responsible for that, but if you want to impress me, and you can work it into a synthesis on your exam. Okay? Just write allylsilane nucleophiles. Okay, so oxidations. So So from an oxidation standpoint, what we're going to do is we're going to oxidize alcohols, right? And this is where I think Max was saying earlier, this is where some of the confusion can come, because you can often confuse the reagents that lead to the aldehyde, say for example, with a reduction and the epoxidation. So the sort of thought is the aldehyde, and so it's very common for people to sort of do that same thing. So, but one of the sort of things that you should think about with PCC, right, and these sort of chromium-based reagents, if you sort of recognize that PCC is a sort of organic soluble chromium reagent, then you can sort of make that analogy to chromium trioxide and how these are all sort of oxidizing agents, right? So PCC is sort of in a way, it is a kind of like an analog, right, of Jones reagent in a way. It's just a organic soluble version of it. Okay, so again, from a primary alcohol, right, we can go to either the carboxylic acid or the aldehyde, right? And so if we want to go to the acid, right, we can use Jones reagents. But in fact, in line with what we just said about PCC, it might be worth it for you guys to sort of, instead of just remembering Jones reagent, I know, again, similar to like LAH, I know it can come off the tongue fairly easy. It may be worth it to remember the reagents because that might help you keep these all ordered. And so, again, Jones reagent is chromium-based. There's a couple ways that you can think about this. You can either go to the chromic acid, but generally what you do is it's chromium trioxide and H2SO4. Okay? And in the case of PCC, I actually didn't show this to you guys, but maybe it's worth it to show it to you guys. PCC is actually, it's called pyridinium. So PCC stands for pyridinium. Chlorochromate. Yeah, so it's pyridinium chlorochromate, and so I'll just show you guys really quickly what it is. Let me make sure I get it right. What you do is you take actually chromium trioxide. So it's also chromium trioxide based, so again, you can sort of relate it to this. And so what you do is you take chromium trioxide, HCl, and pyridine, right, the pyridinium. And so what pyridine is it's an amine, it's an aromatic amine base. So it's like benzene with just a nitrogen in there. And what happens is this forms a new organic soluble chromium complex that looks like this. It's basically CrO3Cl minus, right, and pyridinium HCl plus. And what makes this, so that's pyridine, the protonated version of that is pyridinium, and then what you have is chlorochromate, okay? And so the thing about this sort of salt here is that because you have this kind of big greasy pyridine part, again, you guys sort of learned about solubility, likes dissolving likes. Well, one of the ways that we can take, say, salts, quote-unquote salts, right, and get them to be organic soluble is to have a lot of carbon, hydrogen, grease to it. So this is soluble in dichloromethane, right? So that's one of the advantages to this. So this is PCC. Okay, and so again, the advantage is that you can keep it dry, you run it over molecular sieves, whereas Jones reagent you have to use in water, right? And so what that allows you to do, again, is never get to that hydrate. If you don't get to the hydrate, you don't oxidize up, right? Okay, so we just sort of think about the difference between these two. Like, yes for this one, no for down here. Right, so it doesn't go to the hydrate in the case of PCC. It does go to the hydrate in the case of the Jones. Again, because in the Jones, it's a water-soluble reagent. You run it in aqueous solutions. PCC, you run it in the absence of water. And in fact, if you don't have good, say, molecular sieves, you're not doing a good job of keeping it dry, and there is adventitious water in there, sometimes you can get carboxylic acid impurities. And so it's all about sort of keeping it dry. And so again, that's organic soluble. That's the advantage to it. Okay, so I think that's it. So that's a lot of reactions, right? We're almost done, right? That was 2 days worth of reactions, and we just sort of took us 45 minutes to recap it, right? So I get it that it's a lot going on here, but hopefully you guys can stay on top of this stuff, and you're at least close to being in a position where you can start doing synthesis. So I would argue that by this point you really should have all or the majority of the reactions down, so you can start doing synthesis problems. Oh, sorry, and I just didn't bring up, guys. So if this is a secondary alcohol, it really doesn't matter, right? Because they can only go to the ketone. So I really didn't mention that. If it's a secondary alcohol, you can't go to the ketone. So it's, or sorry, you can't. You can only go to the ketone. You can't go to the acid, right? All right, so let's do some synthesis problems. I'll put up one that's going to require retrosynthetic analysis, and then I'll put up a couple where maybe retrosynthetic analysis might not be the best use. You guys decide. Okay? So the one that I'm going to start with is going to invoke a lot of the chemistry that we've learned. And so if you want to, say, start from only ethanol, right? And I'm asking you guys to come up with a synthesis where you generate butanoic acid, okay? Okay, so what you guys got to do is you got to synthesize butanoic acid, and what you want to do is you want to synthesize this, and ethanol is going to be the only starting material that you're going to want to use. Okay? So from a synthesis standpoint, again, in a situation like this, there's a couple ways that you can do it. And again, over time, what you might notice is that if you're given a particular compound, you might start to see two steps. You might start to combine reactions and see a couple steps. And so you might be able to start from here and move forward. But I think by and large, retrosynthesis can often be the first way to think about them. If you're good at retrosynthesis, you can also often use retrosynthesis to break this down fairly quickly. Okay? And so in this case, what you guys have is a carboxylic acid. Okay? And so one of the first questions that you might want to ask is, how do you make a carboxylic acid? Right? There's a couple ways that we can make them. Right? But they both kind of involve what? What's that? Yeah, well, you can go to an alcohol, or, and we really didn't discuss this, we did. I mean, I guess it's kind of implied, right? You can get to a carboxylic acid from an alcohol. Or we could go to something else, right? What's this sort of other oxidation state where you could still oxidize up to the carboxylic acid? Yeah, I mean, well, what would that be called? It's not a ketone, but it's what? An aldehyde, right? So you can choose either or, right? The point is that you can oxidize up the alcohol all the way to the carboxylic acid, or maybe the aldehyde might be a better starting material for you. So you could start from the aldehyde. It really doesn't matter. It turns out that for both of them, you could get to the final product. One might end up being shorter than the other, but we're really not testing you guys on brevity of synthesis at this point. The challenge is get to the final compound. Okay, so I would gather that the majority of you guys probably would have started from the alcohol, right? And so the question then here becomes, how might we make that alcohol? And this is tricky, right? Because we got to start from ethanol, right? And so it might be worth it to sort of look at this molecule and ask ourselves, well, where's the carbon-carbon bond that we're eventually going to want to break?
Oh, yeah, I think I know what this is.
Right? As we're sort of thinking backwards, that's the carbon-carbon bond that we want to break. Okay? And so we're at an alcohol, right? And so there's a couple ways that we can make that. There's a very direct way that we can go to. But if you guys can't think about it, then there might be other ways that we can make that bond as well. You could imagine going from an alkyne. You could imagine, there's a couple different ways that we could think about this. But if we want to sort of make that bond, we do have a way that we might be able to make that directly right now. Right? And how would we do that? Epoxide. Okay? Okay? And so what you would do from the epoxide is you would take some sort of carbon-based nucleophile, right? And you would treat it with the epoxide. Okay? Now the question that I have is, do we know how to make this compound here from ethanol?
Yeah.
Do we? We might learn eventually, and in fact we'll learn next week. So we may want to choose to use a slightly different nucleophile. But let's ask ourselves, before we go down that road, let's ask ourselves about the epoxide. Let's ask ourselves if we can make the epoxide from the alcohol using chemistry that we know. So MCPBA, we'll make that. And what does it come from?
Alkene.
From an alkene. And can we make that alcohol? Can we make that alkene from ethanol?
Yes.
How would we do that? Acid and heat. So we would do a dehydration. Okay, good. So now we know that we can make, right? So sulfuric acid or some type of acid and heat it up, and you'll eliminate the water. Basically, the point being that we're going to drive away the alcohol. Okay, so now from this guy, again, you guys will learn how to make this nucleophile, and we'll learn it next class. But as we have right now, we don't really know how to make that carbon-based nucleophile. There's only one type of carbon-based nucleophile that we've really learned how to make. And what is that? Acetylene. Right? And so at this point, again, it's not always a linear process when you're trying to solve synthesis, and that's one of the things. Like when I'm up here going through these, this is just sort of a journey, going through all this. But the thing is that we don't know how to make this. But what we do know how to make, right, is an acetylene-based nucleophile. Okay? And I would think that this might be a good way to do it. However, when you react these two together, we're not going to get this. Right? What are we going to get? If we react these two together, right. Okay, now is that a bad thing? Why? Exactly, right? So we can reduce, so that can be our retron, right? So what we can do is, how do we do that reduction? Palladium on carbon, not hydrogen on palladium. But yeah, so palladium on, no, it kind of is hydrogen on palladium. The hydrogen gets absorbed in palladium. So yeah, so palladium on carbon and hydrogen, right? Okay? And so this is one of these situations where you might be stuck there, but then you can sort of maybe reason your way out of it, right? So it's never, a synthesis problem isn't necessarily always going to be in the forward direction. It's never necessarily going to be always in the backward direction. You have to sort of keep an open mind and problem solve, right? That's what this is all about, right? Okay, so now the question is, we were able to make this epoxide from ethanol. Now the question is, can we make this alkyne from ethanol? Okay, well, how do we make this? How do we make this guy, right? We'll make that from the acetylene and a base. NH2. Okay, and how would we make double elimination? And maybe I'll just go in this direction because In fact, again, you could go right from here to here using an extra equivalent because it's the same stuff that used to deprotonate. And then this would just come from the alkene. Right? Which again, we can make from dehydration. Okay, so again, this is a fairly long synthesis problem. Certainly, it's good to sort of reflect on these reactions you're going through the synthesis. So you do need to have some type of synthesis background. Yes?
Could you use acetylene and bromine alcohol or bromine alcohol?
Let's discuss that, right? So
protect the alcohol just so it wouldn't.
So that's where I was going, in a way, I think. Okay? So this is how we get there from the alcohol, right? And when you're doing synthesis problems, one of the nice things is that there are infinite number of ways that you can do them. And so you'll find it's not uncommon, right, for you to be studying with a partner, and they'll come up with one synthesis, and you'll come up with a completely different synthesis, and then maybe whoever has the quicker one can have bragging rights. But in this case, this is one option, right? But as we were doing our retrosynthetic analysis, we can imagine starting from this aldehyde as well. And so let's ask ourselves, could the aldehyde actually be better precursor than the acetylene, right? And so how can we make an aldehyde? But okay, let me ask you a different question then, because I think you're there. So what would be the sort of, what would be the precursor? What could we make an aldehyde from?
It's like an alkyne.
Alkyne. Right? But it's not HgSO4, right? That would be the ketone, like you were saying, yeah. So what you would need to use is what? Hydrogenation oxidation, right? You would need to do the opposite one. So you're right that you're adding water across a double bond, but you want to add, you're halfway there. You want to add it the other way. And now this goes back to what you were saying. So now we have our alkyne right there, right? And so how would we make this alkyne? Well, now we might be able to make this from, by breaking that bond, right? In which case we have this alkyne base nucleophile, right? And bromoethane, right? Bromoethane we can make, right? Bromoethane, how do we make bromoethane? We could either make it from HBr, right? Well, we can make it from the alkene, but we could also make it right from the alcohol with either PBr3 or HBr. Whichever one works. Yeah, I mean, I don't know. Doesn't matter. Or, not, sorry. Right? Okay, so now we're back to the alcohol, and we sort of discussed earlier that we can make this, in the last synthesis that was intermediate. So again, let's just sort of go through this. We can make this from what? The dihalide. Through double elimination. Right? And then this would come from the alkene, right? And again, that alkene could come from the alcohol. So again, acid and heat. Okay, so again, they're roughly equivalent. I think this one was a little bit more efficient, right, than the last one, maybe by a couple steps. It certainly looks like it conserved on board space a bit. But again, the point is that there's many different ways that we can get to that sort of final product. Okay. So by and large, I think I've been focusing on retrosynthetic analysis because I think that oftentimes retrosynthetic analysis is one of the best ways to sort of reason synthesis. But oftentimes, again, you sort of have to balance both. And so we've been trying to work on thinking backwards to an extent, and that's kind of what I wanted to start with. But sometimes problems require thinking forward. Sometimes retrosynthetic analysis might not necessarily be the go-to way, right? And there's really no way to sort of know at the get-go which one you want to use, and it's likely that you're going to use a combination. So another type of synthesis problem that you'll often see will be one where you get something that's maybe a little bit more complex, right, than ethanol or something straightforward, and you're sort of asked the question, right? I want to make that compound, and how could I go? This is another way that sometimes synthesis problems are sort of asked of you guys. I want to go from here to here. How might I go through that synthesis? Okay, and so these are often stepwise, usually a little bit less, perhaps, than the ones that require retrosynthesis. And sometimes these are just as easy to think about in the forward direction as they can be in the reverse direction. So you can oftentimes use a combination, but again, it sort of would depend upon how many steps would be in between. Okay? So from this guy here, I think, again, there's a couple of different ways that you could do this. I think the best way, I think I can see, the quickest way could be actually a two-step process. Okay? And again, there's really no right way to go about this, but let's sort of think about, I want you guys to spend a couple minutes maybe thinking about how you might get there if some people have some ideas. So go ahead and just, you guys start working it out, spend a couple minutes thinking about how you might go from an alcohol to this sort of exocyclic alkene. So notice that you've added a carbon, right? And so at some point you're going to have to think about a carbon-carbon bond forming reaction. But you're also going to need to have that alkene in there. So in this case, you can use any other carbon-based source, obviously. You're not asked to degrade this down to a single one carbon unit that you could then add in. So you can use anything. The point is start with this, get to that. You can use any carbon compound at your disposal except this. You were the only one that got that. Guess it wasn't that funny. All right. I said that you can't use this as a reagent. And I got one snicker.
Yes.
2 Snickers. Okay, so anybody got any ideas about, anybody want to throw up an idea of how they might make this? Yeah.
Use old analysis somewhere there to go backwards.
Well, I think you're asking a different question. Maybe we can ask, that'll be the second follow-up. How do we go from here to here? What I'm asking is how do we go from here to here? O's analysis, I think, would be a good way if we want to go the reverse. Yeah.
You can try H2SO4 to eliminate that the water.
Okay, so you want the final step to be, so you want to do retrosynthesis here.
Well, no, I'm starting with that one. So I'm adding a hydrogen onto the oxygen and the hydrogen.
Okay, so what you want to do is you want to treat this with H2SO4, okay? And you just want to eliminate. So that's H2SO4 and heat. Okay, so now we're at that alkene.
Yeah. And then I want to try to do that double bond, and I'll do can I do a hydrogen?
A what?
I'll also use the O from the H2SO4, and I'll take that out. Well, no.
Yeah, I think you're.
Okay.
Do we want to do that elimination first?
No.
Yeah, I mean, we might lose a handle here that might be useful. But this is kind of how this happens, right? It's a trial and error. You sort of go, does this help me get to anything that looks like it might be more helpful? Maybe not. Yes?
We can make it into a ketone first.
Okay, so one option would be, again, to make this into a ketone. How would we make this into a ketone? What reagent would we use to make that into a ketone? Jones reagent, right? So chromium trioxide and H2SO4 or Jones reagent.
And then you can present it to an alkene.
Right. Right, how do we do that? Vittig, right, exactly. So we would do the Vittig rule. Yeah. So this was the synthesis that I was thinking about, right? So it kind of seems silly to now show the many other ways that you could do it, but one thing that you might imagine is if you forgot how to go, let's pretend that your Vittig's not working. Vittig is just not working. The world is out of triphenylphosphine. I can't make this. But I need to get here. Can you guys think of another way that might not involve avidic? What's that? Zinc? Methyl zinc? Where'd you learn that?
She said zinc.
Yeah, I think you can, actually.
She said zinc.
Oh, yeah. Well, what's going to happen if you treat that with zinc and mercury? Yeah, you're going to sort of lose your handle, right? So oftentimes it's that functional group that you're going to be using to change things. So to do chemistry from an alkane is very difficult, right? But we've learned that we can, we just sort of showed one way that we can make a carbon-carbon bond, right? But what's the other way that we can make carbon-carbon bonds from ketones? What's that? Not epoxide. Well, no, but how do we make that carbon-carbon bond? What's that? Yeah, some type of nucleophile, right? So R2 minus, I think was just said, but in this case, what would be the R2? How many carbons do we want to add? 1, right? So it would be Me minus, right? So it would be CH3 minus. And again, we'll discuss, there's usually a counter-ion, methyl lithium, say for example, would be common. So we'll discuss the synthesis of these tomorrow, but we weren't asked that. In this case, we don't have to know how to make it. Again, we know that there's carbon-based nucleophiles. You take carbon, you put that negative charge on it, it's going to behave as a nucleophile. Right? And now we've made that carbon-carbon bond. Right, now we've sort of made the carbon-carbon bond, and now the question is, can we convert this molecule into an alkene? Right? And can we do it in a single step, or do we need to do multiple steps to do this? Say it again? Right, so you have to get rid of the OH in some way. Certainly, that's going to need to be, effectively, what's the difference between this molecule and this molecule? The double bond, but formally, what's missing? The OH and the hydrogen, so water, so H2O, right? Because we're missing one of these hydrogens, right? Because there's only 2 CH3s there, right? And we're missing the OH. So formally, we're going to lose water. Okay, well, what's one of the ways, do we know a way that we can get rid of water, right, and form an alkene from, say, an alcohol? Okay, so, right. But here's the problem. If we're going to do that elimination, where's the double bond going to be? Right. Why? It's more stable, right? An internal alkene is more stable. So this would be one option, right? But we would have a regioselectivity. We'd have the wrong alkene. There's a couple different possible eliminations. So what do we want to do? Hold on. What's that? From where? So hydroboration is on a what? An alkene. We don't have any alkenes here. Yes? We can, but is T-butyl, wait, say it again? Right, so the T-butyl, so T-butoxide, right? So what would T-butoxide promote an elimination of this? Why not? You need a good leaving group. Well, so let's make it into one, right? Right? So how would we make this into a good leaving group? Sarah, you're absolutely right. T-butoxide is what we want to do that elimination, but an alcohol isn't a good enough leaving group. And so what we need to do is we need to convert this into a leaving group in one of the several different ways that we know. HBr, sure. PBr3, those are going to make bromides. What if we wanted a chloride? SOCl2. What if we wanted a tosylate? Whoa, tosylate. The sulfonates. Right, those SO, right? So you have the SO2RCl, right? right? You can make it into some type of sulfonate, either a tosylate or a mesylate. The point is, you can turn that into something many different ways. It really doesn't matter. Let's go with what the first person said. HBr. Right? And then we can take this, right, and we can treat this with the T-butoxide. And that's going to do the elimination to lead to the less substituted alkene. Okay? So again, your synthesis problem, there's a couple different ways to get there. And again, I can't teach you guys synthesis. I can go through some synthesis problems with you guys and get you guys thinking about it. But in terms of getting comfortable with it, you guys sort of have to practice on your own. We're going to do one more shot. We're just going to do one more quick synthesis problem in the remaining 5 minutes. And it's not going to be that long. I just think it's kind of interesting, right? Like, we learned the mechanisms of the reaction are reversible, but what about, can we go in the reverse direction, which was brought up before? Let's say we wanted to get the alcohol, right? Let's say we had the alkene and we wanted to get to the alcohol. Just hearing people shout out things. So what's the hydrogenation going to do? Sometimes, again, I'm going to draw this up here. Sometimes you have an idea. Let's just draw it out and see what happens. Is that going to lead to this alcohol? It's going to lead to that alcohol. So it will lead to an alcohol, right? But sometimes it's worth it to just draw out the product, because that's not an uncommon mistake. You're like, oh, I have an alkene, I want to get to the alcohol, and you don't actually pay attention to your carbon count, right? So that's a common mistake. So that's fine. This is why we do this, right? So hydrogenation certainly leads to an alcohol, but it leads to the wrong alcohol. Let's look at overall what we want to do here. How many carbons are in the product? How many 6, and how many in the starting group? 7. So we need to lose a carbon, right? So we need to lose a carbon. What is one of the only ways that we know to cleave a carbon-carbon bond? Ozonolysis, right? And what does ozonolysis run on? Ozone, no, but what do you convert? What's the starting material in ozonolysis? What do you ozonolize? A double bond, right? So we've got a double bond here, right? And so if we did this reaction with ozonolysis and say dimethyl sulfide or something like that, what's the product of this going to be? Right? A carbonyl, right? What's the other part of it? Yeah, the formaldehyde, but we don't care about that. We just care about this, because that's got the 6 carbons that we want. Okay? Yes?
That means it's going to be a horrible yield.
Yes, I was.
No, moles to moles. Right? All your carbons, you might get lower mass recovery, right? Like a yield, remember, is moles. Right? So you're losing mass, but your yield is based upon the moles, and so you're not losing any moles. Right? Okay, so how do we get from here to here? LAH, sodium borohydride, platinum hydrogen. We can go there is the point. Let's just say sodium borohydride. And recognize that there's a couple other ways that we could do that. Okay? Alright, so next week we'll learn a few more reactions. Start working on synthesis, get these reactions together, and